On January 18th, the sun fired a shockwave at the moon, and the moon couldn't stop it. No magnetic field, no atmosphere. The billion-ton wall of plasma hit the surface at full velocity, ripping atoms straight out of the rock. NOAA classified the radiation storm as S4, severe, the most intense since 2003. And for the forecasters watching the data stream into Boulder, Colorado, that lunar impact wasn't the story. It was the preview, because roughly 24 hours later, that same plasma reached Earth. The moon was the canary, and the canary just told us the air in the mine shaft is the worst it's been in over 2 decades, during a solar cycle that every major prediction panel said would be average. If what the moon just absorbed has you locked in, take a second and hit subscribe to Orbital View. We're tracking solar cycle 25 through every eruption, every geomagnetic warning, every infrastructure test this star throws at us. Drop a comment and tell me, did you see the aurora in January? How far south were you? I read every one. Here's where this investigation goes. A shock wave that crossed 93 million miles of open space and physically ripped atoms off the lunar surface, and what the instruments recorded when it hit. The 9-hour blackout that plunged 6 million people into darkness in 90 seconds flat. The 4 astronauts who flew through the radiation environment that storm created just 10 weeks later. And the grid vulnerability that a Lloyd's of London report quietly priced at $2 trillion. A number almost nobody outside the insurance industry has read. Let's get into it. Part 1. The blast that hit the moon. First. On January 18th, 2026 at 1809 hours Coordinated Universal Time, the sun did something that the European Space Agency's monitoring network flagged within minutes. An X-class solar flare, the most extreme classification in the taxonomy, erupted from an active sunspot region on the solar disk. And it didn't erupt alone. Riding behind the electromagnetic flash, accelerating through the corona at roughly 1 million miles per hour, came the part that matters more: a coronal mass ejection. A billion-ton cloud of magnetized plasma, expanding in every direction, aimed almost directly at the inner solar system. I need you to hold 2 timelines in your head because they run on different clocks, and the difference between them is the whole story. The electromagnetic radiation from that flare, the X-rays, the ultraviolet burst, traveled at the speed of light. It reached the moon in 1.3 seconds. It reached Earth 8 minutes later. That's the speed of light timeline. But the coronal mass ejection, the physical wall of charged particles, moves slower, much slower. Depending on conditions, that cloud takes anywhere from 18 hours to several days to cross the same distance. And here's the thing that most coverage missed entirely. The moon, on January 18th, was positioned such that it intercepted that shockwave before Earth did. Think about what that means. The moon has no magnetic field worth measuring. It has no atmosphere in any meaningful sense. What scientists call the lunar exosphere is so thin it's essentially individual atoms bouncing around above the surface, a gas envelope so sparse it's almost indistinguishable from the vacuum of space. NASA describes it as what you get when you whack a dirty rug with a broom. Particles knocked free by impact, drifting through near emptiness. When a coronal mass ejection hits Earth, our magnetosphere absorbs the blow, redirects the charged particles, channels them toward the poles. That's what makes the aurora. The magnetic field is a shield. It bends, it flexes, but it holds. The moon doesn't have that shield. When a CME hits the moon, it hits the surface, directly. No deflection, no absorption, no mercy. The solar wind particles, protons, helium ions, and during a CME, heavier ions like oxygen and iron that normally aren't present in significant quantities in the solar wind, slam into the lunar regolith at hundreds of kilometers per second. And they don't just land there. They knock atoms loose. Sodium, potassium, calcium, magnesium, elements bound in the minerals of the lunar soil, get physically ejected by the impact. Scientists call this process sputtering. I want you to think of it as sandblasting. The sun is sandblasting the moon, and during a CME, the sandblaster gets turned up by an order of magnitude. NOAA's GOES 19 satellite, sitting in geostationary orbit at 35,000 kilometers altitude, staring at the sun with its solar ultraviolet imager and particle detectors running continuously, confirmed what the instruments were showing. By January 19th, the solar radiation storm had intensified to S4 on NOAA's space weather scales. Severe. That's the second highest rating on a 5-point scale, and the Space Weather Prediction Center in Boulder, Colorado, the forecasters who sit in a room that looks like a miniature mission control, surrounded by real-time solar wind data streaming from 1,000,000 miles away, put out a bulletin that used language I want you to read carefully. This event, they said, was rare, and it exceeded the intensity of the October 2003 Halloween space weather storms. The Halloween storms had been the benchmark for 2 decades. January 2026 just moved the benchmark, so the moon got hit first. And then Earth's turn came. The aurora appeared on January 19th across Europe. Not the subtle, photographic, exposure-only shimmer that aurora chasers in Scotland or Scandinavia chase on good nights. This was visible, vivid, unmistakable. Observers in France reported green and crimson bands stretching across the sky over Brittany. In Belgium, the lights were visible from Brussels. Social media filled with photographs from latitudes that almost never see the aurora. Latitudes where the magnetic field lines don't normally channel enough particle flux to excite atmospheric gases. The G4 geomagnetic storm, KP Index 8, severe on NOAA's 5-point scale, guessed compressed the auroral oval southward, pushing the boundary where incoming solar particles interact with the upper atmosphere deep into mid-latitudes. The NOAA Space Weather Prediction Center's 3-day forecast, issued on January 21st, noted that the greatest observed 3-hour KP over the past 24 hours was 8E G4. They projected continued storm conditions as the CME effects gradually waned, but the grid held. Power systems in North America and Europe weathered the geomagnetic disturbance without major failures. Satellite operators reported disruptions, not losses. HF radio communications degraded but didn't go silent. The system, at every level, absorbed what the sun delivered, and so the story faded from the news within days, replaced by whatever came next. I need you to understand why that's not the end of the story. It's the beginning. Part 2. The exosphere that vanished. Before I tell you what happened when that shockwave reached Earth, I need to take you deeper into what happened when it reached the moon. Because the lunar impact isn't just a curiosity, it's a diagnostic tool. And nobody in the mainstream coverage treated it that way. The moon's exosphere, that thin scattering of atoms, exists in a constant state of creation and destruction. Every second, micrometeorites slam into the lunar surface at velocities of 10 to 70 kilometers per second, vaporizing bits of regolith and lofting atoms into ballistic trajectories. Meanwhile, the solar wind delivers its steady rain of protons, each one capable of knocking a surface atom loose through the sputtering process. Some of those ejected atoms escape lunar gravity entirely and drift off into interplanetary space. Others arc back down to the surface. The exosphere is a living, breathing, well, not breathing, nothing breathes in a vacuum, a continuously refreshed envelope balanced between creation and loss. And January 2026 was, by every available measure, the strongest gust since October 2003. To understand why that matters, start with what the moon's atmosphere actually is, because precision here matters. I hesitate to even call it an atmosphere because the word conjures images of weather systems, of layers of gas thick enough to scatter light and sustain breathing. The lunar exosphere is nothing like that. It is, by every practical measure, a vacuum. The total mass of gas surrounding the moon is estimated at roughly 10 metric tons. 10 metric tons. That's less than the air inside a single large commercial aircraft hangar. Spread that over a sphere 2,160 miles in diameter, and you have a gas envelope so sparse that any given particle can travel for kilometers before encountering another particle. The mean free path, the average distance between collisions, is longer than the radius of the moon itself. Each atom is essentially on its own, tracing a ballistic arc from the surface to wherever gravity or the solar wind sends it. This exosphere exists in a constant state of creation and destruction, a balance between processes that eject atoms from the surface and processes that remove them. Every second, micrometeorites slam into the lunar regolith at velocities of 10 to 70 kilometers per second, vaporizing bits of soil and lofting atoms upward. Sunlight drives another process called photon-stimulated desorption. Ultraviolet photons hit surface minerals and knock loosely bound atoms free. Thermal desorption adds another contribution, especially on the day side where surface temperatures reach 250 degrees Fahrenheit. And then there's the solar wind, delivering its steady rain of protons, each one capable of sputtering a surface atom if it hits with enough energy and at the right angle. On the removal side, some ejected atoms achieve escape velocity, about 2.4 kilometers per second on the Moon compared to 11 on Earth, and drift off into interplanetary space permanently. Others follow ballistic arcs that bring them back to the surface where they stick until the next impact or photon frees them again. The solar wind itself sweeps exospheric particles downstream, carrying them away from the Moon's surface and into the interplanetary medium. The exosphere is a dynamic system, constantly replenished and constantly depleted, hovering at a density determined by the balance between these competing processes. And then a CME arrives, and the balance shifts violently. The TU Wien and University of Bern study, published in Communications, Earth and Environment in 2025, rewrote our understanding of one side of that balance. Their experiment took real Apollo 16 lunar soil, sample 68,501, collected by astronauts from the Descartes Highlands in 1972. They bombarded this genuine moon dust with hydrogen and helium ions at solar wind speeds in a laboratory setting, and the sputter yields they measured were up to 10 times lower than what previous exosphere models had assumed, a full order of magnitude. The reason is elegant: the lunar surface fights back. Over billions of years of micrometeorite bombardment, the regolith has developed a roughness and porosity at every scale. Craters within craters within craters, from the micron level to the kilometer level, with grain surfaces that are irregular, pitted, and covered in nanophase iron particles created by previous space weathering. When a solar wind proton hits this surface, it often strikes at an oblique angle, ricocheting off grain facets instead of transferring its full energy to a surface atom. The roughness dissipates the incoming energy across multiple collisions, reducing the probability that any single atom gets enough of a kick to escape. But that protection has limits. It works against normal solar wind, the steady, relatively gentle proton drizzle the sun delivers on a quiet day. During a CME, the incoming bombardment changes character so dramatically that the surface roughness can't compensate. The density spikes by a factor of 10 or more. The heavier ions arrive: oxygen at 16 times proton mass, iron at 56 times proton mass, helium at 4 times, all traveling at the same bulk velocity as the protons, but carrying proportionally more kinetic energy. And the enhanced magnetic field within the CME can temporarily compress the solar wind flux into the surface at angles that the roughness can't deflect. Rosemary Killen at NASA's Goddard Space Flight Center modeled this transition in detail. Her simulations predicted that species normally hovering just below detection thresholds, calcium, magnesium, aluminum, would be lofted above detectability during a CME passage. The entire composition of the exosphere would shift. Instead of the sodium and potassium-dominated envelope that orbiting instruments normally detect, a CME would produce a brief, intense bloom of heavier elements blasted from the deeper mineral matrix of the regolith. Picture a gust of wind hitting a sand dune. Under normal conditions, only the loosest grains on top blow away, but hurricane-force winds rip grains from deeper layers, changing what the dune releases into the air. Nobody flew a LADEE-type instrument during January 2026. That's a gap in our observational coverage that matters. LADEE, the Lunar Atmosphere and Dust Environment Explorer, was purpose-built for this measurement, with a neutral mass spectrometer and a UV spectrometer tuned to detect exactly the species Killen's models predicted would spike during a CME. It operated from October 2013 through April 2014, during solar maximum of cycle 24. But cycle 24 was weak. The strongest events LAD encountered were modest by cycle 25 standards. What we do have is the Lunar Reconnaissance Orbiter, still circling the Moon since 2009 with its LAMP instrument measuring ultraviolet emissions. And we have the Artemis probes, 2 spacecraft, originally part of the Themis magnetospheric mission, redirected to locations near the Moon in 2008, measuring charged particles swept from the lunar environment. Those instruments were in position during January's CME passage. The raw telemetry is in the processing pipeline at Goddard and at the Space Sciences Laboratory at UC Berkeley. Precision about what we know and don't know here, because precision about that boundary is the most valuable thing I can offer. The full analysis of January's lunar exospheric response hasn't been published. Peer review takes time, and responsible science doesn't rush to conclusions. What we know from Killen's pre-event modeling is that a CME of the intensity NOAA classified, exceeding the 2003 benchmark, should have produced the strongest sputtering enhancement the modern instrument suite has ever observed. The data to confirm or complicate that prediction exists. The publications are coming, and when they arrive, they will give us an unprecedented measurement of what happens when the strongest storm in 20 years hits a surface with zero protection. Part 3. The cycle that broke the forecast. I have to be completely honest with you here, because the honest answer is also the interesting one. The scientists got this wrong. Not slightly wrong, significantly wrong. And the direction of the error matters enormously. In 2019, the Solar Cycle Prediction Panel, an international team of researchers convened jointly by NOAA, NASA, and the International Space Environment Service, issued their consensus forecast for Solar Cycle 25. These aren't junior analysts. This panel includes some of the most experienced solar physicists in the world. They use physical models, precursor methods, statistical inference, machine learning, and decades of institutional knowledge. The prediction was specific. They expected the cycle to peak between November 2024 and March 2026, with a smoothed monthly sunspot number between 105 and 125. They called it average, similar to cycle 24, which had been one of the weakest cycles in a century. That prediction is now definitively wrong. By February 2024, the smooth monthly sunspot number had already reached 137 Dürers, clearly outside the panel's predicted range and still climbing. The daily sunspot number was regularly exceeding 250. Since April 2024, large and complex sunspot groups had been appearing on the solar disk with a frequency and intensity that the forecast didn't anticipate, and the flaring activity was staggering. By late February 2026, Solar Cycle 25 had produced 1,690 M-class flares, 165 flares in the M5 to M9 range, and 101 X-class flares. 101, those are the most powerful category of solar flare, and this cycle was supposed to be average. So what happened? How did an international panel of solar physicists miss by this much? The answer reveals something uncomfortable about how we predict solar behavior, and it connects directly to the grid vulnerability I'm going to walk you through in the next section. Scott McIntosh at the National Center for Atmospheric Research had published a competing prediction. His 2023 revision forecast, a peak sunspot number of 184, plus or minus $17, roughly 50% higher than the consensus. His method tracked what he called terminator events, the endpoints of magnetic activity bands from the previous cycle, which he argued were predictive of the next cycle's amplitude. When the terminator arrived earlier than expected, McIntosh's model predicted a stronger cycle. The consensus panel had dismissed this approach. The Sun sided with McIntosh. And this isn't just an academic scorecard. I need you to see why the direction of the error matters. A stronger solar cycle means more CMEs, more X-class flares, more S4 radiation storms, like January 2026, more geomagnetic disturbances reaching the KP8 and KP9 levels that take down power grids. The forecast error wasn't neutral. It was an error in the direction of underestimating the threat. And it means the infrastructure planning, the grid hardening timelines, the satellite shielding schedules, all of it was calibrated against a sun that was supposed to be quieter than the sun we actually got. The strongest Earth-facing flare of the cycle so far was an X9 on October 3rd, 2024. For reference, the X-class scale is logarithmic. An X9 releases 9 times the energy of an X1, and the flare that preceded the January 2026 CME was an X-class event that drove the most intense radiation storm in over 2 decades. So hold that. The sun is running hotter than predicted. The errors are consistently in the same direction, due underestimation. And the consequences of that underestimation compound. With every month, the cycle continues at elevated levels. But the mechanics of solar cycle prediction deserve more scrutiny because the failure to predict cycle 25's amplitude isn't just an interesting scientific footnote. It's a systemic vulnerability that cascades through every risk assessment built on cycle forecasts. Solar cycle prediction uses roughly 4 categories of methods. Precursor methods look for signals in the declining phase of the previous cycle that correlate with the amplitude of the next one. The strength of the polar magnetic field near solar minimum, for example, has historically been a reliable predictor. A strong polar field tends to precede a strong cycle. Statistical methods use the historical record of past cycles to fit curves and extrapolate. Physics-based models attempt to simulate the sun's internal magnetic dynamo, the convective churning of plasma beneath the surface that generates, amplifies, and eventually reverses the solar magnetic field. In machine learning, approaches train algorithms on the historical sunspot record to identify patterns. The 2019 panel used all of these approaches. The precursor methods pointed to a week-to-average cycle. The statistical methods agreed. The physics-based models were divided, but mostly aligned with a modest peak. The consensus coalesced around a smooth sunspot, maximum of 115, peaking in July 2025. McIntosh's alternative was structurally different. His terminator hypothesis argues that the key signal isn't the polar field strength at minimum, but the timing of the terminator C, the moment when the magnetic activity bands from the old cycle finally cancel at the equator. An earlier terminator implies a faster magnetic cycle, which correlates with a stronger upcoming cycle. When the cycle 24 terminator arrived earlier than the consensus models expected, McIntosh's framework predicted a significantly stronger cycle 25. The sun validated McIntosh. Not perfectly, his specific peak prediction of 184 plus or minus 17 overshoots the observed smooth maximum of about $160, but far more accurately than the consensus 115. The actual cycle fell roughly between the consensus and McIntosh, but much closer to McIntosh. The consensus missed low by roughly 40%. That's not a fine-tuning error. That's a categorical miss in the direction that matters most for risk assessment, and the implications radiate outward. Grid vulnerability assessments that use the consensus forecast to estimate the probability of severe storms during cycle 25 underestimated that probability. Satellite operators who scheduled maintenance and shielding upgrades based on expected activity levels may have miscalibrated their timelines. Radiation exposure models for human spaceflight, including the models used to plan Artemis, were built against an expected solar environment that turned out to be substantially more active than predicted. The panel's updated prediction, released in stages as observations diverged from the original forecast, did narrow the gap. By 2023, they had revised upward, but the revised predictions still trailed the observations, and the institutional lag between issuing a prediction and having that prediction reflected in operational planning is measured in years. A prediction issued in 2019 shapes planning decisions through 2023 and beyond. By the time the prediction is corrected, the decisions it informed have already been made. This isn't a failure of competence. The solar dynamo is genuinely difficult to predict. The relevant physics occurs deep inside the sun, in regions we can't directly observe. The historical record of cycles is short, about 25 well-observed cycles, which limits the statistical power of any trend analysis. And the sun's magnetic field exhibits a stochastic component that may be irreducibly unpredictable, the way individual weather events are unpredictable even when climate trends are clear. But the fact that the prediction difficulty is understandable doesn't reduce the consequences of the prediction error. The infrastructure decisions that flow from cycle forecasts are real. The risk they embody is real. And when the forecast says average and the sun says exceptional, the margin of safety shrinks without anyone updating the margin. Part 4. 90 Seconds to Darkness. I want to take you back 37 years because what happened on one cold night in Quebec is the clearest proof that the threat we're talking about isn't theoretical. It isn't a modeling exercise. It already happened. And the infrastructure it destroyed was simpler, far simpler than what we depend on now. March 13th, 1989, 2:45 in the morning, Eastern Time. The temperature outside was below zero. 6 million people were asleep in homes heated by electric baseboards, electric furnaces, electric everything, because Quebec's grid was, and largely still is, one of the most electrically dependent power systems in North America. The province generates almost all its electricity from hydroelectric dams in the James Bay region, hundreds of kilometers to the north, and sends it south through some of the longest high-voltage transmission lines on the continent. A geomagnetic storm had been building for days. The source was Sunspot Region 5395 Deuce, one of the largest active regions ever recorded, so big you could see it with the naked eye through proper solar filters. It had been erupting for over a week, sending multiple CMEs toward Earth. The DST index, which measures how much the Earth's magnetic field has been compressed and distorted by incoming solar plasma, plunged to negative 589 nanotesla. That number made it the strongest geomagnetic storm since standardized measurement indices had been in use, going back to 1932. And here's what happened in Quebec in the 90 seconds that followed. The geomagnetically induced currents flowing through the Canadian Shield, that massive slab of Precambrian rock, 3 billion years old, one of the most resistive geological formations on the continent, couldn't dissipate into the ground the way they would in more conductive geology. Picture trying to pour water into concrete versus sand. The rock was too resistive, so the current found a better path. It flowed into the high-voltage transmission lines, the 750 kilovolt lines running from James Bay. It flowed into the transformers, and it overwhelmed the protective systems. Static VAR compensators at the Chibougamau and La Vérendrye substations tripped first. These are the devices that regulate voltage on long transmission lines, smoothing out fluctuations that would otherwise destabilize the grid. The GIC-generated harmonics saturated them. They couldn't distinguish the geomagnetic signal from a system fault, so they did what they were designed to do. They disconnected, and when they disconnected, the voltage on the transmission lines started oscillating. Power swings built. Within seconds, 5 transmission lines from James Bay tripped simultaneously. 9,450 megawatts of generation capacity vanished in an instant. The grid was carrying a load of 21,350 megawatts at that moment. It couldn't absorb a loss that sudden, that large, that geographically concentrated. The cascade propagated outward from the James Bay corridor. Churchill Falls went down. Manic Outerdies went down. Substation after substation tripped protective breakers that were doing exactly what they were supposed to do in the presence of abnormal electrical conditions. Except the abnormal conditions were coming from space, not from a fault in the wire. Within 90 seconds, the entire Hydro-Quebec grid was dark. Total system collapse. 6 million people lost power. They lost heat. In March, in Quebec, for 9 hours. The economic cost, according to a study published in Advances in Space Research, was approximately $13.2 billion. The human cost, 9 hours without heat in sub-zero temperatures, hospitals running on backup generators, water treatment plants offline, the elderly and vulnerable left in the dark, is harder to quantify and rarely attempted. But here's the part of this story that doesn't get told enough. David Boatler, who heads the Space Weather Group at Natural Resources Canada, has been clear about this. The March '89 storm was severe, but it was not a Carrington-class event, not even close. On the scale of what the sun is capable of delivering, Quebec was a warning shot, and the warning shot took down an entire provincial grid in a minute and a half. Let me walk you deeper into that night. The details matter because they transform this from a statistic into a story, and the story is the thing that makes the risk real. March 13th, 1989, 2 in the morning, Eastern Time. The province of Quebec is asleep. 6 million people in a vast territory spanning over 600,000 square miles, most of them concentrated in the cities of Montreal and Quebec City, but many scattered across smaller communities connected to the same grid. Outside, the temperature hovers well below freezing. March in Quebec is not spring. It is the deep tail end of winter, and the heating systems that keep every building in the province habitable are running continuously. Those heating systems are overwhelmingly electric. This isn't an accident of preference, it's a consequence of geography and economics. Quebec generates virtually all of its electricity from hydroelectric dams in the James Bay region, hundreds of kilometers to the north. Cheap, abundant hydropower made electric heating the default choice. The province built its entire residential and commercial heating infrastructure around the assumption that the grid would always be there. By 1989, the peak winter demand on the Hydro-Quebec system regularly exceeded 21,000 megawatts, almost all of it for heat. The power reached southern Quebec through some of the longest high-voltage transmission lines in North America. 735 kilovolt lines, among the highest voltage in the world at that time, stretching from the La Grande complex at James Bay to the load centers in the south. These lines were the arteries of the system. If they failed, the southern half of the province had no alternative power supply of comparable scale. And 500 miles above, the magnetosphere was being hammered. Sunspot region 5395 had been erupting for over a week. It was enormous, visible to the naked eye through proper solar filters, which almost never happens. Multiple CMEs had been launched toward Earth in the preceding days, and the magnetosphere was already disturbed when the strongest pulse arrived on March 13th. The DST index, think of it as a blood pressure reading for Earth's magnetic field, where negative values indicate compression and distress, plunged to negative 589 nanotesla. For reference, a value of negative 50 is a moderate storm. Negative 100 is intense. Negative 589 was and remains the deepest measurement since standardized indices were adopted in 1932. At 2:45 a.m., the geomagnetically induced currents flowing through the Canadian Shield reached a critical threshold. And here I need to explain why Quebec's geology made it uniquely vulnerable, because this isn't just background detail. It's the mechanism that turned a solar storm into a human catastrophe. The Canadian Shield is one of the oldest geological formations on Earth. Precambrian rock, 3 billion years old, the exposed root of an ancient mountain range worn flat by time. It underlies most of Quebec and much of central and northern Canada. And from an electrical standpoint, it is almost perfectly resistive. Current doesn't flow through it easily. It's like trying to push water through concrete. When a geomagnetic storm induces electric currents in the Earth, those currents need a path. In areas with conductive sedimentary geology, deep layers of wet, mineral-rich soil, the currents can flow through the ground with relative ease. The ground absorbs them. But on the Canadian Shield, the ground says no. The current bounces off the resistive rock and finds the next best path, which is the high-voltage transmission lines and the grounding connections of transformers strung across the landscape above the rock. So the current flowed into the grid. It flowed through the 735 kilovolt transmission lines. It entered the transformers through their grounding connections, and it overwhelmed the voltage regulation equipment. The static VAR compensators at the Chibougamau and La Vérendrye substations, devices designed to smooth voltage fluctuations on long transmission lines, were the first to fail. The GIC-generated harmonics saturated their protective systems. The compensators couldn't distinguish between a geomagnetic signal and a system fault, because from the equipment's perspective, the electrical signature looked the same: abnormal current flowing where it shouldn't be. The compensators did what they were designed to do. They disconnected. And when they disconnected, the voltage on the James Bay transmission lines began oscillating. Without the compensators damping the fluctuations, power swings built rapidly. The oscillations propagated down the lines. Within seconds, not minutes, seconds, 5 transmission lines from James Bay tripped simultaneously. 9,450 megawatts of generation capacity vanished in an instant. The grid was carrying 21,350 megawatts of load. It had just lost 44% of its supply in a heartbeat. The cascade was inevitable. Churchill Falls in Labrador went down. The Manic Outards complex on the north shore of the St. Lawrence went down. Substation after substation across the province tripped breakers, each disconnection adding to the imbalance, each imbalance triggering the next disconnection. Within 90 seconds, and I keep coming back to that number because I need you to feel how fast 90 seconds is when 6 million people's heat depends on what happens. The entire Hydro-Quebec grid was dark. Total system collapse. Every traffic light in Montreal went black. Every hospital switched to backup generators. Every elevator stopped. Every water treatment plant lost its pumps. Every building in the province began cooling toward the outdoor temperature, which was well below freezing. 9 hours later, Hydro-Quebec began restoring power. By midday, most of the system was back online. But the economic cost, estimated at $13.2 billion in a study published in Advances in Space Research, only captures the quantifiable damage. It doesn't capture the grandmother in a fourth-floor walk-up in Montreal's Plateau neighborhood who couldn't get down the stairs in the dark. It doesn't capture the cardiac patient whose monitoring equipment went silent. It doesn't capture the psychological impact of waking up in a modern city and discovering that modernity has a switch, and something, just flipped it. David Boatler at Natural Resources Canada has devoted much of his career to understanding what happened that night. And the thing he keeps saying, the thing I want you to carry forward through the rest of this investigation is this. March 89 was not the worst case. It was not a Carrington-class event. The DST index hit negative 589. The Carrington event's DSC is estimated between negative 800 and negative 1750 nanotesla. The 1989 storm was a warning shot, a demonstration, and the demonstration took down an entire provincial grid in 90 seconds. Part 5. The Canary with No Shield. Now, I need to take you back to the moon because the moon is doing something for us that no other body in the inner solar system can do, and almost nobody is talking about it. Think of the moon as a canary in a coal mine, but this canary doesn't have a cage. It doesn't have a gas mask. When the toxic air comes, the canary takes the full dose and you get to watch what happens before the same air reaches you. Except in this case, the toxic air is a wall of magnetized plasma, and the delay between when the moon gets hit and when Earth gets hit is your warning window. Hours, sometimes a day, sometimes less. And what the moon showed us in January 2026 was that the air in the mine shaft was the worst it had been in over 20 years. The S4 radiation storm that NOAA classified, that rare event, that benchmark exceeding event, hit the moon without any magnetic deflection, without any atmospheric absorption, without any of the protections that Earth takes for granted. Every proton, every heavy ion, every chunk of magnetized plasma that the coronal mass ejection carried across 93 million miles of space landed on the lunar surface at full velocity. The solar wind doesn't slow down when it hits the moon. It doesn't get redirected to the poles. It arrives, and the surface absorbs it. The instruments recorded it. The Lunar Reconnaissance Orbiter, an SUV-sized spacecraft that's been circling the moon since 2009 with 7 science instruments continuously gathering data, was there. Its Lyman Alpha Mapping Project Instrument, LAMP, measures ultraviolet emissions from the exosphere, which spike when sputtering intensifies. The Artemis probes, 2 spacecraft originally part of the Themis magnetospheric mission, redirected to the moon when their primary assignment ended in 2008, sit near the moon, measuring the charged particles that get swept away from the lunar exosphere by the solar wind. Those instruments registered what January's CME did to the moon's gas envelope. The data pipeline runs through NASA's Goddard Space Flight Center and the Space Sciences Laboratory at UC Berkeley, and the compound connection that ties the lunar science to the human story. The same plasma that sandblasted the moon, the same CME, the same shockwave, reached Earth's magnetosphere roughly 24 hours later. And when it arrived, the KP index hit 8. That's a G4 storm. Severe. The aurora was visible across Europe at latitudes where it almost never appears. Observers in France, in Belgium, in locations that hadn't seen northern lights like that in years. The moon took the unfiltered hit. Earth took the filtered version, and the filtered version still produced the strongest geomagnetic storm in over 2 years. And that compound connection, the moon taking the unfiltered hit, Earth taking the filtered version, and the filtered version still producing the strongest geomagnetic storm in over 2 years, raises a question that connects directly to the next part of this investigation. Because 10 weeks after January's storm, 4 human beings launched toward the moon, and the sun was not done. Part 6. The astronauts in the crosshairs. 10 weeks after the January storm, 10 weeks, 4 human beings launched from Kennedy Space Center on the most powerful rocket ever to carry a crew. Artemis II, Commander Reed Wiseman, pilot Victor Glover, mission specialists Christina Koch and Jeremy Hansen, April 1st, 2026, 6:35 in the evening, Eastern Time. Lifted by the Space Launch System, a vehicle standing 322 feet tall, generating 8.8 million pounds of thrust, designed to hurl its crew beyond the protection of Earth's magnetosphere and into the deep space radiation environment. And the sun was not done. Late on March 29th, 36 hours before launch, NASA's Solar Dynamics Observatory captured an X-1.4 class flare erupting from an active sunspot. An X-class event, the most powerful classification. The flare produced a coronal mass ejection aimed generally toward Earth. It triggered a radio blackout over parts of Asia and Australia. And it raised a question that should have been louder than it was. Should you launch 4 astronauts toward the moon through an active radiation environment during the strongest solar cycle in decades? NASA's answer was clear. Amit Kshatriya, the associate administrator, told reporters at Kennedy Space Center that the agency wasn't expecting the CME to cause any effects on the mission. The mission management team gave the official go decision. The launch proceeded, and the crew flew. They performed the translunar injection burn on April 2nd at 7:49 in the evening, Eastern Time. That burn accelerated Orion to 39,472 kilometers per hour, fast enough to escape Earth's gravitational influence and coast toward the moon. On April 6th, they flew around the moon's far side at a distance of 6,545 kilometers, spending about 40 minutes out of communication as the moon blocked their signal from Earth. They observed the lunar darkness, the stars beyond, visible planets. They became the first humans in over 50 years to see the far side of the moon with their own eyes. On April 10th, at 5:07 in the afternoon, Pacific Time, Orion splashed down in the Pacific Ocean off the coast of San Diego. All 4 crew members were recovered safely. By every public metric, the mission was a success. But here's what I need you to hold alongside that success. Those 4 astronauts were, for 10 days, the most radiation-exposed human beings on Earth, or rather, off Earth. The International Space Station orbits at roughly 400 kilometers altitude, well within the magnetosphere's protective bubble. Artemis II flew 695,000 miles round trip, the majority of it outside the magnetosphere entirely, during a solar cycle producing X-class flares at a rate the forecasters didn't predict. The radiation dosimetry from that flight, the detailed particle counts, the tissue-equivalent dose measurements from Orion's onboard instruments will take months to fully analyze, and the question it will answer connects to the central thesis of this entire investigation. What is the actual radiation environment that the sun is producing right now? Because if the answer is significantly worse than the models predicted, the same models, built by the same forecasting infrastructure that already missed the amplitude of cycle 25 due, then the implications cascade into Artemis III, the mission that's supposed to actually land astronauts on the lunar surface, into the Gateway Station planned for lunar orbit, into every human mission beyond low Earth orbit for the rest of this decade. ESA was explicit about this connection. Their monitoring center, in their assessment of the January storm, stated directly that good monitoring of the radiation environment would be critical for the Artemis missions carrying astronauts to the moon. That wasn't a throwaway line. That was a European Space Agency telling the world that the radiation environment their instruments were measuring was severe enough to raise operational questions about the most high-profile crewed mission in half a century. The moon is telling us something. And the humans we're sending toward it are part of the story whether we frame it that way or not. To understand why, consider that the history of astronaut radiation exposure is shorter and more unsettling than most people realize, and it connects directly to what the moon absorbs during events like January 2026. During the Apollo program, 12 humans walked on the lunar surface across 6 missions between 1969 and 1972. Every one of those missions flew during the declining phase of solar cycle 20 Dars, a cycle that was moderately active but well past its maximum by the time Apollo 11 launched in July 69. The mission planners knew the radiation risk. They had no magnetospheric protection once they left low Earth orbit. The Apollo spacecraft offered minimal shielding. The command module walls were aluminum, effective against some particles but transparent to the highest energy galactic cosmic rays, and largely inadequate against a major solar energetic particle event. And they got lucky. Between 1969 and 72, no major solar particle event struck during any Apollo mission's lunar transit or surface stay. The closest call came in August 1972, between Apollo 16 in April and Apollo 17 in December, when a massive solar flare produced a particle event that would have delivered a potentially lethal dose to any astronaut on the lunar surface. If Apollo 16 had launched 4 months later, or Apollo 17 4 months earlier, the crew would have been caught in it. The timing was fortuitous. It was not a result of superior forecasting. Now project that history onto today. Solar Cycle 25 has produced 101 X-class flares by late February 2026. The January S4 event exceeded the 2003 benchmarks, and Artemis II flew a 10-day mission through this environment, relying on Orion's enhanced radiation shielding. Improvements over Apollo, certainly, with a storm shelter in the crew module and more advanced monitoring systems, but still fundamentally exposed to whatever the sun chose to deliver during those 10 days. The Orion spacecraft carries a hybrid electronic radiation assessor, which provides real-time dose rate monitoring. It also carries passive dosimeters and a crew radiation monitoring system. The data from these instruments will quantify, for the first time in over 50 years, the actual radiation environment experienced by humans in translunar space. And it will do so during a solar cycle that nobody predicted correctly. If the numbers come back lower than expected, that's good news for Artemis III. If they come back higher, the mission planning for lunar surface operations, where astronauts will be exposed for days, not hours, on a surface that has no magnetosphere and an exosphere that provides zero shielding, will need fundamental revision. The sputtering that Killen modeled, the sandblasting that strips atoms from the lunar regolith, is driven by the same particles that pose a radiation hazard to human tissue. The mechanism that erodes the moon's surface is the mechanism that can damage human DNA. And the January storm showed us that the mechanism is running hotter than predicted. Tackle Part 7. The Physics of Sandblasting. A world. Let me take you inside the sputtering mechanism, because the mechanics are genuinely remarkable, and without understanding them, the scale of what January demonstrated won't land the way it needs to. Picture a billiard table. A cue ball, that's a solar wind proton, slams into a racked set of balls. Some of the balls in the rack get knocked loose and scatter across the felt. That's sputtering at its simplest. An incoming ion transfers kinetic energy to atoms on a surface, and if that energy exceeds the binding energy holding those atoms in place, they get ejected. They fly off. In the case of the moon, those ejected atoms become part of the exosphere, that barely there envelope of gas clinging to the lunar surface through nothing but gravity and the lack of anywhere else to go. But during a coronal mass ejection, the cue ball changes. Instead of lightweight protons, hydrogen nuclei, the smallest and most common particle in the solar wind, the CME delivers a cocktail that includes helium nuclei, oxygen ions, and even iron. These are heavier, dramatically heavier. An iron ion has 56 times the mass of a proton, and in a CME, these particles aren't just present, they're moving at the same velocities as the protons. Same speed, 56 times the mass. The kinetic energy scales linearly with mass. So an iron ion in a CME hits the lunar surface with 56 times the energy per particle compared to a normal solar wind proton. And it gets worse. The density of the solar wind during a CME can spike by a factor of 10 or more above quiet conditions. So you have heavier ions hitting harder and more of them hitting per second. It's not just switching from a BB gun to a rifle. It's switching from a BB gun to a rifle and firing 10 times faster. The billiard table analogy gets you 80% of the way toward understanding sputtering, but the remaining 20%, the part that distinguishes a qualitative understanding from a quantitative one, requires going inside the laboratory where the TU Wien team did their work, because the experimental design reveals something about how much we didn't know about a process we thought we understood. The standard method for measuring sputter yields, for decades, was to use analog materials. Researchers would bombard olivine crystals, or pyroxene minerals, or synthetic glass compositions that approximated the chemical makeup of the lunar regolith. The problem is that chemical composition is only half the story. The physical structure of the surface matters enormously, and the lunar surface has a physical structure unlike anything that can be synthesized in a laboratory. 4.5 billion years of micrometeorite bombardment have given the regolith a structure that is, at every scale, fractured, porous, and irregular. Individual grains are coated in amorphous rims, thin layers of disordered glass created by previous ion bombardment, studded with nanophase iron particles, and shaped by impacts into forms that bear no resemblance to the smooth, faceted crystals you find in a geology textbook. The bulk porosity of the regolith, the fraction of space versus solid, runs around 40 to 50% in the upper layers. Imagine a bowl of cornflakes versus a bowl of marbles. The cornflakes have far more surface irregularity and far more void space between them. The lunar regolith is more like the cornflakes. When the TU Wien team bombarded actual Apollo 16 soil with hydrogen and helium ions at solar wind energies, roughly 1 kilo-electron-volt per nucleon for protons, 4 kilo-electron-volts per nucleon for alpha particles. They were, for the first time, capturing the effect of this real surface structure. The incoming ions didn't hit a flat, smooth mineral face. They hit a landscape of irregular grains, pores, shadows, and overhangs. Many ions struck grain surfaces at glancing angles and scattered without transferring enough energy to eject an atom. Others penetrated into pores and deposited their energy deep in the grain structure where the sputtered atoms couldn't escape. The net effect was a 10 times reduction in sputter yield compared to what flat surface mineral analog experiments had measured. This result has implications beyond the moon. Mercury's surface is bombarded by solar wind at higher intensities than the moon's. Mercury is closer to the sun, and its weak magnetic field channels solar wind onto the surface at the cusp regions. The ESA-JAXA Bepi-Colombo mission, currently in orbit around Mercury, is studying that planet's exosphere with instruments that rely on sputter yield estimates to interpret what they measure. If the real yields for Mercury's regolith are also significantly lower than analog-based estimates, the interpretation of Bepi-Colombo's exospheric data would need revision, and the same logic applies in reverse for CME conditions. If normal sputter yields are 10 times lower than assumed, but CME yields are dramatically enhanced by heavier ions and higher densities, then the contrast between quiet and storm conditions is even sharper than previous models suggested. The exosphere doesn't just increase during a CME, it transforms from a nearly undetectable baseline to a measurable atmospheric event. The signal-to-noise ratio between quiet sun and CME passage becomes enormous, which is exactly what makes the moon such a powerful diagnostic tool for measuring CME intensity. Every X-class flare, every CME that washes over the lunar surface, writes its signature in the exospheric data. The signature during quiet conditions is barely above the noise floor. The signature during a storm leaps above it, and the ratio between the two tells us, with a precision that no other measurement provides, how much more energetic the storm was compared to normal conditions. The moon isn't just absorbing the blow, it's calibrating it. Kyak, Part 8, The Sentinel at the Lagrange Point. And this is where the story takes a turn that most coverage completely misses. Because the moon isn't the only thing sitting between us and the sun with an inadequate shield. Our entire early warning system for geomagnetic storms depends on a small constellation of aging spacecraft hovering at a gravitational sweet spot 1 million miles from Earth. Discover, the Deep Space Climate Observatory. It orbits the Sun at the first Lagrange point, L1, a position roughly 1.5 million kilometers sunward of Earth, where the gravitational pull of the Sun and Earth balance out, allowing a spacecraft to hover in a stable orbit. From L1, solar wind reaches Discover 15 to 60 minutes before it reaches Earth. That gap is the entirety of our tactical warning time for geomagnetic storms. Think about that number, 15 to 60 minutes. A billion-ton cloud of magnetized plasma is hurtling toward Earth, and our early warning system, the system that tells power grid operators to open transformer disconnects, that tells satellite controllers to safe mode vulnerable systems, that tells airlines to reroute polar flights. That system gives us, at best, 1 hour. At worst, a quarter of that. Discover carries a Faraday cup that measures solar wind speed, temperature, and density. It carries a magnetometer that samples the interplanetary magnetic field. When a CME approaches, Discover measures its properties in real time, and the most critical of those properties, the one that determines whether a CME impact will produce a minor geomagnetic disturbance or a grid-threatening storm, is the orientation of the magnetic field inside the approaching plasma cloud. A CME with a southward-oriented magnetic field, one that opposes Earth's northward-pointing field, couples with the magnetosphere far more efficiently. It opens the magnetic shield. It lets energy pour in. A northward field, by contrast, slides past with minimal interaction, and you don't know the orientation until the CME reaches L1. Models can estimate it. The WSA Enlil simulation that SWPC runs operationally can predict arrival time and density, but the magnetic field orientation inside a CME is notoriously difficult to forecast. It's the single most important parameter, and it's the one we can't reliably determine until the plasma actually touches our Sentinel spacecraft. Discover launched in February 2015. It was designed for a 5-year mission. It's now in year 11. In July 2025, a software anomaly silenced it temporarily. NOAA does maintain a backup. The Advanced Composition Explorer, ACE, which also orbits L1. But ACE launched in 1997. It's approaching 3 decades of operation, well beyond any reasonable design lifetime. Both spacecraft are living on borrowed time. The replacement, NOAA's space weather, follow-on satellite, SWFO L1, executed its final engine burn in January 2026, reaching its orbital position at L1 just days after the S4 storm. The timing of that arrival borders on theatrical, but SWFO L1 is not yet fully operational. Its coronagraph instruments are being commissioned. The differential imagery from its compact coronagraph became available on SWPC's website only recently. The transition from Discover to SWFO L1 as the primary operational sentinel is underway. It is not complete, so this is the picture. The Sun is in a cycle that exceeded predictions. The storms it's producing are exceeding benchmarks. And our early warning system is a patchwork of aging spacecraft, one of which nearly failed 6 months ago, being slowly replaced by a successor that isn't fully online yet. This isn't a conspiracy. It's a procurement timeline colliding with a solar cycle. And the procurement story itself reveals a gap between the speed of solar activity and the speed of institutional decision-making that borders on structural. Discover's origin story is instructive. The spacecraft was originally conceived in 1998 as Triana, an Earth observation mission championed by Vice President Al Gore to provide a continuous full-disk image of the sunlit Earth. The concept was simple: put a camera at L1 and let the world watch its own planet in real time. It would have been, in Gore's vision, a kind of environmental consciousness tool. Congress defunded it. The spacecraft was built, fully assembled, tested, and ready for launch, but it was put into storage at Goddard Space Flight Center. For years, a flight-ready spacecraft sat in a clean room while the political winds shifted. In 2008, a committee determined that Triana, now renamed Discover, could be the optimal solution for meeting NOAA and USAF space weather requirements. The spacecraft was pulled from storage, refurbished, fitted with updated solar wind instruments, and launched in February 2015 on a SpaceX Falcon 9. From conception to launch, 17 years. From storage to launch, 7 years. The spacecraft was designed for a 5-year mission. It has now been operating for over 11 years. And the replacement, SWFO-L1, took its own winding path through the federal procurement process before reaching L1 in January 2026. Compare those timescales to the solar cycle. Solar cycle 25 began in December 2019. It was expected to peak between late 2024 and early 2026. The strongest events are already occurring. SWFO L1 arrived at L1 in January 2026, barely in time for the peak, and not yet fully commissioned. If the cycle had peaked earlier, as some revised predictions suggested, we would have faced peak solar activity with our primary Sentinel operating beyond its design lifetime and its replacement still in transit. This is not a critique of the individuals involved. The engineers who kept DSCOVR running past its design life did exceptional work. The teams commissioning SWFO L1 are working diligently. The problem is systemic. The procurement timelines for space weather monitoring infrastructure are measured in decades, while the threats they monitor can emerge in hours. The mismatch is inherent in how we fund and build these systems, and no amount of individual dedication fixes a structural gap. The Japanese Space Agency, JAXA, has proposed complementary monitoring concepts. The European Space Agency has its own L1 mission planning. The Chinese National Space Administration has expressed interest in space weather monitoring at L5, which would provide a different viewing angle of CMEs approaching Earth. A truly robust early warning system would involve multiple spacecraft at multiple vantage points, providing redundancy and angular diversity. What we have instead is a single operational spacecraft at L1, with a backup that's 29 years old and a successor that's still commissioning its instruments. The Moon, by contrast, is always there. It's been there for 4.5 billion years. It doesn't need fuel. It doesn't suffer software anomalies. It doesn't require congressional appropriations. It absorbs every CME at full intensity and records the result in its exosphere, in its surface chemistry, in the particle environment measured by whatever instruments happen to be orbiting it. The Moon is the monitoring system that doesn't fail. The problem is that we haven't fully built the instrument suite to read what it's telling us. LaDi flew for 6 months and was intentionally crashed into the surface. LRO is still there, but its instruments weren't optimized for exospheric monitoring during extreme events. The Artemis probes measure the particle environment, but they're repurposed spacecraft operating at the edge of their design parameters. So the monitoring gap isn't just at L1, it's at the Moon itself. We have a natural laboratory that performs a Carrington test every time the sun erupts, and we've staffed the laboratory with instruments designed for other purposes. Part 9. The Current That Melts Transformers. This is where two threads of this investigation finally meet, and where the compound nature of the threat becomes unavoidable. What connects the Moon's stripped exosphere to the Quebec blackout to the aging Sentinel at L1 is a single physical mechanism, geomagnetically induced currents. And the weak point in the chain, the component that fails first, fails catastrophically, and takes the longest to replace, is the extra high voltage transformer. A large power transformer is not something you can order on Amazon. I'm not being flippant. This matters operationally. These are custom-built machines. Some weigh over 400 tons. They're manufactured by a handful of companies worldwide: ABB, Siemens, Hyundai, a few others. The lead time for a new one, from order to installation, typically runs 12 to 18 months under normal conditions. Some estimates put it at 24 months when demand spikes. There is no strategic national reserve of these transformers in the United States. A 2012 Department of Energy report flagged this. The supply is limited. Most are imported. Now layer the mechanism on top of that logistics reality. When a geomagnetic storm drives quasi-direct current through the power grid, those currents flow through the grounding connections of transformers. Transformers are designed for alternating current at 50 or 60 hertz. They are emphatically not designed for quasi-DC. The GIC pushes the transformer's magnetic core into a condition called half-cycle saturation. Imagine the magnetic field in the core being pulled to one side on every cycle, like a swing being pushed higher and higher in one direction. The core can no longer efficiently channel magnetic flux. The excess energy converts to heat. Intense, concentrated heat in the windings, in the core, in the insulating oil. Sustained GIC exposure can permanently damage a transformer in minutes. And unlike a tripped breaker, which can be reset with the flip of a switch, a burned transformer is a burned transformer. You need a new one, and the new one is 12 to 18 months away, manufactured overseas, transported by specialized heavy haul equipment, installed by a crew that has to lift 400 tons with surgical precision. The Lloyds of London report, published in collaboration with atmospheric and environmental research, modeled the scenario with uncomfortable specificity. For a Carrington-class geomagnetic storm hitting the North American grid, they estimated 20 to 40 million people without power for durations ranging from 16 days to 1 to 2 years. Economic damages between $600 billion and $2.6 trillion. Even the low end of that range exceeds the total insured losses from Hurricane Katrina by a factor of 4. And the geographic vulnerability isn't uniform. It follows the geology. The USGS has been mapping this worst geoelectric hazard assessment, they call it. Areas underlain by resistive igneous and metamorphic rock produce higher GIC levels because the current can't dissipate into the ground and instead flows through the grid. The Canadian Shield, the Appalachian Crystalline Complex, parts of the upper Midwest. These zones overlap with dense population centers and critical infrastructure corridors. The geology that's billions of years old is shaping the vulnerability of a grid that's decades old. Quebec sits on the Canadian Shield. That's not a coincidence. It's a geophysical vulnerability that was known before March '89. The grid just wasn't hardened against it until after 6 million people spent 9 hours in the dark. The Canadian government invested $1.2 billion after that night, blocking capacitors, series compensation on transmission lines, recalibrated trip levels. Those upgrades worked. Hydro-Quebec's modern grid can handle a 1 in 100-year geomagnetic event, but the cost of protecting just the 1,000 most vulnerable transformers in North America with GIC blocking capacitors is estimated at roughly $100 million, about $100,000 per device. $100 million. In the context of the North American electricity sector's annual capital expenditure, that's a rounding error, and the deployment is incomplete. To understand why that incompleteness matters so much, you need to see the relationship between geology and grid vulnerability is the compound connection that turns a solar storm from a space phenomenon into a human infrastructure crisis. I've mentioned the Canadian Shield, but the vulnerability map is larger and more specific than most people realize, and the USGS has been methodically assembling it. Geoelectric hazard assessment works like this. Researchers measure or model the electrical conductivity of the Earth's crust and upper mantle at every point on the map. Areas with deep, wet sedimentary basins, places like the Mississippi River Valley, the Great Plains, the Gulf Coast, tend to have higher conductivity. The ground absorbs GIC relatively well. The current dissipates before it can build up dangerous levels in the grid above. Areas with shallow, resistive, crystalline bedrock tell a different story. The Canadian Shield, the Appalachian crystalline complex running from Georgia to Maine, the Superior Craton underlying Minnesota, Wisconsin, and Michigan, parts of the Piedmont region, the Colorado Plateau. In these zones, the ground refuses to carry the current, and the current has no choice but to flow through whatever conductive paths exist above the rock, which means the power lines and pipeline networks that crisscross the landscape. The USGS has published geoelectric field maps that show, for a given geomagnetic disturbance level, how strong the induced electric fields would be at the surface, and the variation is dramatic. The same G4 storm that produces modest GIC in Mississippi can produce dangerous GIC levels in Maine or Minnesota. The transformer at the end of a long transmission line in northern Wisconsin sees a fundamentally different threat environment than an identical transformer in Louisiana, even during the same solar storm. And the grid doesn't respect these geological boundaries any more than the storm does. The North American power grid is interconnected. Power flows across state lines, across geological boundaries, through transformers that may be sitting on resistive rock even though the generation source is on conductive ground. The vulnerability is distributed unevenly, but the consequences cascade through a system that is connected everywhere. The blocking capacitors that protect transformers from GIC, the $100,000 devices I mentioned earlier, work by interrupting the quasi-DC pathway through the transformer's grounding connection. They block the GIC while allowing normal AC grounding to function. Simple, effective, proven, and not universally deployed. Why not? The answer is frustratingly mundane. Grid operators prioritize capital expenditure against threats they can see and quantify with recent experience. Hurricanes destroy transmission infrastructure regularly. Ice storms take down lines. Equipment ages and must be replaced. GIC protection competes for capital allocation against threats that happen every year versus a threat that might happen once in a career. The rational economic calculus at the individual utility level often favors the near-term investment, but the rational calculus at the civilizational level is different. Because when the storm comes, it doesn't hit one utility. It hits every utility under the auroral oval simultaneously. The mutual aid agreements that work after hurricanes, where unaffected utilities send crews and equipment to help affected ones, don't function when everyone is affected at once. And the transformer supply chain that can handle 1 or 2 replacements per year at any given manufacturer cannot handle 50 or 100 simultaneous orders. This is the compound nature of the threat. The storm is physical. The vulnerability is geological. The consequences are logistical. And the delay between losing a transformer and replacing it, 12 to 18 months, is the gap into which the human consequences accumulate. Weeks without power, water systems failing, supply chains breaking, perishable medications spoiling, medical equipment going dark. The moon doesn't have this problem. The moon doesn't have a grid. When the CME hits the lunar surface, atoms get sputtered into the exosphere and drift away. Nothing breaks, nothing goes dark. The damage is atomic scale and continuous and, from a human perspective, irrelevant to the moon's function. But the moon's response to the CME tells us exactly how hard the sun hit. And the question for us isn't how hard the surface was hit. It's whether the shield that stands between us and that same hit is strong enough, and whether the infrastructure behind the shield is resilient enough for the fraction of the energy that gets through. The answer, for the current grid configuration, depends on which of the 3 interpretations you hold. And the evidence I've shown you, all of it, doesn't cleanly resolve that question. It narrows it, it constrains it, but it doesn't close it. That's the honest answer, and the honest answer is also the urgent one. Mid-video rehook. If you've made it this far, I want to tell you where this goes next, because the second half of this investigation is where the threads converge, and the picture they form is one I haven't seen assembled anywhere else. So far, I've shown you the event, the January CME, the S4 storm, the moon absorbing the unshielded impact. I've shown you the historical precedent, Quebec going dark in 90 seconds. I've shown you the astronauts who flew through this radiation environment 10 weeks later. And I've shown you the warning system, aging spacecraft, a single point of failure, a successor that's still commissioning its instruments. Now I'm going to show you the frequency question. How often storms this severe actually occur, and why the answer has far more uncertainty than the number that gets cited. I'm going to show you the Carrington event, not as a historical anecdote, but as a measured ceiling for what the sun has already demonstrated it can do. I'm going to take apart the conspiracy claims with specific physics and then show you the one alternative framing that actually has peer-reviewed scientific support. And I'm going to present three interpretations of everything I've shown you, one that says the system is working, one that says the gap is real and growing, and one that I keep coming back to myself. Let's continue. That's Part 10, the frequency question, and the compound connection that almost nobody outside the solar physics community is making publicly. The question isn't whether a Carrington-class event will happen again. The question is how often events of that magnitude occur, because the answer determines whether the current level of grid hardening is adequate or dangerously insufficient. NOAA has estimated that Carrington-class storms occur roughly once every 500 years. That number gets cited frequently. It sounds reassuring. 500 years is a long time, but that estimate deserves scrutiny, and when you apply it, the reassurance fades quickly. The 500-year return period is derived from a very short observational record. We've been systematically monitoring solar activity for roughly 170 years. We've had satellite instruments for roughly 50. Estimating a 500-year return period from 50 to 170 years of data is like estimating the 100-year flood from 5 years of river gauge readings. The confidence interval on that estimate is enormous, and it runs in both directions. The true return period could be longer than 500 years, or it could be substantially shorter. Second, storms half as intense as the Carrington event occur roughly every 50 years. That's NOAA's own assessment. March 1989 is generally considered to be in that range. We've already had one of those during the modern grid era, and it caused a blackout affecting 6 million people. Third, the solar cycle we're in right now is producing individual events at intensities that the mainstream forecast didn't predict. If the cycle amplitude was underestimated, the probability of extreme events during this cycle was also underestimated. The S4 storm in January was not a Carrington event, but it was more severe than anything since the Halloween storms, and it happened in a cycle the panel called average. Hold these together. Irreplaceable transformers. A sun producing storms at a pace and intensity the forecasts missed. A frequency estimate with enormous uncertainty, and a consequence, trillions of dollars, months to years of disruption that makes the expected value of the risk staggering even at low probabilities. This is the mathematics of catastrophe. The frequency question becomes more complicated and more urgent when you layer compound risk on top of single event risk. A single CME producing a single geomagnetic storm is the standard threat model. Most of the analysis I've cited, the Lloyd's report, the National Academy study, the USGS hazard mapping, evaluates the impact of a single severe event. But the sun doesn't always cooperate with the single event assumption. Look at what actually happened in May 2024. Active region 13664, a massive sunspot complex that dominated the solar disk for weeks, didn't produce a single CME. It produced a sequence, multiple X-class flares, multiple full halo CMEs. Some of them merged in transit, combining their magnetic fields and amplifying their impact. The resulting geomagnetic storm reached G5, the highest level on NOAA's scale, with a KP index of 9. It was the strongest storm since the Halloween events of 2003, and it was driven not by a single eruption, but by a bombardment. The Carrington event itself may have been a compound event. There's evidence that 2 CMEs were involved. A precursor eruption that cleared a path through the ambient solar wind, followed by the main ejection that traveled through the evacuated channel at unprecedented speed. The 17.6-hour transit time may have been possible only because the first CME swept the interplanetary medium clear, reducing the drag on the second. If that's how the worst-case scenario actually plays out, not as a single punch, but as a combination, a 1-2 that arrives in rapid succession before the grid has recovered from the first hit, then the damage estimates need revision upward. A transformer that survives a single period of GIC exposure might not survive two in quick succession. A satellite that weathers one radiation pulse might lose its remaining margin when the second arrives hours later. A power grid that rides through a G4 might fail when the G5 follows before operators can reconfigure. The May 2024 event gave us a preview of compound solar storms during the modern monitoring era. The grid handled it, but the May event, despite reaching G5 briefly, had a key mitigating factor. The interplanetary magnetic field orientation was predominantly northward for significant portions of the storm, limiting the coupling efficiency with Earth's magnetosphere. The aurora was spectacular precisely because the storm was large enough to overcome even partial coupling. A fully southward field orientation, the worst case for geomagnetic coupling, would have produced far more severe GIC levels at ground level. The compound risk extends beyond sequential CMEs. Consider what happens if a severe geomagnetic storm strikes during a heat wave, when electrical demand is at maximum and the grid is already stressed, or during a polar vortex event, when heating demand in the northern tier spikes and natural gas supply chains are already strained. The storm itself doesn't know about the weather on the ground, but the consequences of a blackout during a heat emergency or a cold emergency are categorically worse than a blackout during mild conditions. This is the kind of compound thinking that the fire weather community has been doing for years, layering drought conditions on top of wind events, on top of ignition and probability, to get compound fire risk assessments that individual variables don't capture. The space weather community is beginning to do the same thing, but the integration of ground-level vulnerability with space weather forecasting is still in its early stages. And the moon, again, provides the baseline measurement. The moon doesn't care about compound risk. It has no infrastructure to fail, no population to protect. But the intensity of the CME it absorbs is the starting input for every compound risk calculation. How hard did the sun actually hit? The moon tells you, unfiltered. Then you apply the magnetospheric modulation, the geological conductivity, the grid configuration, the load conditions, the season, the time of day, and you get the human consequence. January the 20 to 26 gave us one data point, one event, one intensity level. The question is how many data points we accumulate before the big one arrives, and whether we use those data points to prepare or whether we file them away the same way we filed away July 2012. Part 11. The Carrington Parallel, 167 years before the January 2026 storm, on September 1st, 1859, Richard Carrington was sketching sunspots at his private observatory in Red Hill, Surrey, when a sudden flash of white light erupted from the sun. He was the first human to observe a solar flare. He noted the time and called for a witness, but by the time someone arrived, the flash was fading. What rode behind that flash, though Carrington couldn't have known, because the concept of a coronal mass ejection wouldn't exist for another century, was the fastest, most massive CME in the modern record. It crossed 93 million miles in approximately 17.6 hours. For context, most CMEs take 2 to 3 days. The Carrington CME arrived in less than 18 hours. The speed implies a velocity of roughly 3,000 kilometers per second. When it hit, the magnetosphere didn't just flex, it buckled. The aurora was visible at the equator, Colombia, the Caribbean, latitudes where the northern lights are as foreign as snow. In the northeastern United States, the sky was so bright that people could read newspapers at midnight. Gold miners in the Rocky Mountains woke at 1 in the morning and started cooking breakfast, convinced the dawn had arrived. The damage hit the telegraph system, the only electrical network spanning any distance in 1859. Operators across North America and Europe reported sparks flying from equipment. Paper caught fire. In some stations, telegraphists disconnected their batteries entirely, and the telegraphs kept working, powered solely by the geomagnetically induced currents flowing through the wires. The atmosphere was generating enough current on its own to drive the system. I bring up Carrington not because I think another one is imminent. I have no evidence of that. I bring it up because it establishes the ceiling. The sun has done this, not theoretically, in documented telegraphically verified fact. And if that CME launched from the sun today, DSCOVR would give us 15 to 60 minutes of warning. Coronagraph observations might detect the launch itself, giving a longer window, if the CME is Earth-directed, if the imagery is clear, if the modeling pipeline process is fast enough, if the forecasters at SWPC in Boulder are watching and interpreting in real time. The margin here isn't comfortable. Walk with me into 1859 because the event that sets the ceiling for what the sun can do deserves more than a summary. It deserves the story. September 1st. The observatory at Redhill sits on a hilltop in Surrey, about 20 miles south of London. Richard Carrington was 33 years old, wealthy from his family's brewery fortune, and had spent the previous 6 years making the most precise daily sunspot observations in the world. He was not a dilettante. His catalog of sunspot positions, compiled through thousands of hours of meticulous sketching, would earn him the gold medal of the Royal Astronomical Society. He took his work seriously. That morning, he projected an image of the solar disk onto a white screen mounted behind his telescope's eyepiece, the standard technique for solar observation. Then and now, because looking directly at the sun through a telescope will permanently destroy your retinas. He was sketching a large, complex sunspot group, cataloged in his records as a region of unusual size and complexity, when at 11:18 a.m. local time, something happened that had never been recorded before. 2 brilliant points of white light appeared within the sunspot group. They were intensely bright, bright enough to be visible even against the glare of the projected solar disk. Carrington was so startled that he ran from the observatory to find a witness, convinced that no one would believe him without corroboration. By the time he returned with someone, the bright points were already fading. The entire event lasted about 5 minutes. What Carrington had witnessed was a white light solar flare, an extremely rare phenomenon in which a flare's optical emission is bright enough to be visible against the photosphere, which is itself blindingly luminous. White light flares represent the most energetic category of solar flares. They are so rare that even today, with continuous satellite monitoring, only a handful are observed per solar cycle. Carrington noted the time and the position on the disk with the precision of a trained observer and published his account in the monthly notices of the Royal Astronomical Society. Independently, another British astronomer named Richard Hodgson observed the same flash from a different location and published a confirming account. 2 independent observers. 2 independent publications. The observation was bulletproof. What they could not see, because the concept didn't exist yet, because the sun's corona wasn't well understood, because nobody knew what a coronal mass ejection was what launched from the sun behind the flare, a wall of magnetized plasma containing billions of tons of solar material, accelerating outward through the corona and into the interplanetary medium. 17.6 hours later, it arrived at Earth. The transit time alone tells you something about the speed. At the Sun-Earth distance of approximately 150 million kilometers, a transit time of 17.6 hours implies a velocity of roughly 2,400 kilometers per second. Most CMEs travel at 400 to 1,000 kilometers per second. The Carrington CME was moving at 2 to 6 times the typical speed. There's a theory about why it was so fast. Solar physicists have proposed that a precursor CME, a smaller eruption from the same active region, may have launched hours or days before the main event, sweeping the interplanetary medium clear of the normal solar wind plasma that would otherwise slow the following CME through aerodynamic drag. The main CME then traveled through this evacuated channel at extraordinary speed, like a freight train on cleared tracks. When the shockwave hit the magnetosphere, the resulting geomagnetic storm was unlike anything in the modern record. The DST index, reconstructed from ground-based magnetometer data at several observatories that were operating in 1859 or Fuchs, has been estimated at anywhere from -800 to -1750 nanotesla. Compare that to March 89's -589. The uncertainty range is itself striking. We're not sure whether the Carrington event was 1.5 times or 3 times more intense than the worst modern storm. Either way, it was in a different category. The aurora reports from that night and the following night are extraordinary. The northern lights were visible at latitudes where they had never been reported before, well into the tropics. Observers in Colombia, in Hawaii, in Cuba reported seeing the sky colored crimson and green. Ship logs from the Caribbean described the aurora as so bright that sailors could read by its light. In the Rocky Mountains, gold miners encamped throughout Colorado and California were roused from sleep by the sky's brightness and began preparing breakfast, genuinely believing that dawn had arrived. The clock said 1 a.m. The sky said otherwise. The human infrastructure impact was limited by the fact that in 1859, the only electrical infrastructure of any scale was the telegraph network, but the effect on that network was dramatic. Telegraph operators across North America and Europe reported sparks shooting from their equipment. The insulation on telegraph lines smoldered. Paper tape caught fire. In several offices, operators received electrical shocks strong enough to be painful. And then the truly remarkable thing happened. At some telegraph stations, operators discovered that if they disconnected their batteries entirely, the telegraph lines continued to function. The geomagnetically induced currents flowing through the wire were strong enough, carrying enough voltage and current to drive the entire system without any external power source. The Earth's disturbed magnetic field, coupled into the telegraph infrastructure by the same GIC mechanism that would take down Quebec's grid 130 years later, was doing the battery's job. The atmosphere had become a generator. This detail matters because it demonstrates the scale of the energy involved in a way that no abstract number can. The GIC from the Carrington event was strong enough to serve as a power supply. In 1859, the only thing that current could damage was telegraph equipment. Today, that same current flowing through a modern power grid would encounter transformers, capacitor banks, relay systems, and semiconductor-based control electronics, all far more sensitive to GIC than a telegraph key and a spool of wire. Part 12. The claims that miss the point. Something needs addressing directly because the people asking deserve an actual answer. Every time the sun produces a major event, every time the aurora lights up mid-latitudes, every time NOAA issues a geomagnetic storm warning, a set of claims circulates. HARP, weather modification, directed energy weapons. The impulse behind these claims deserves more respect than it usually gets. When events are this extreme, this poorly predicted, and this sparsely covered in mainstream media, people look for explanations that match the scale of what they're seeing. The gap between the scale of the event and the scale of the public explanation creates space for alternative narratives. I understand that. I've read the comments. So let me address the most prominent claim with specific physics. HARP, the High Frequency Active Auroral Research Program, is a research facility in Gacona, Alaska. It operates an ionospheric heater, antennas that transmit high-frequency radio waves into the ionosphere. Maximum transmitted power, 3.6 megawatts. A single coronal mass ejection releases energy on the order of 10 to the 25th joules, roughly equivalent to the energy the entire United States consumes in a year. HARP's 3.6 megawatts, running continuously for a year, delivers approximately 1.1 times 10 to the 14th joules. That's 11 orders of magnitude less than a single CME, 100 billion times less. You cannot steer a hurricane with a flashlight. The energy isn't there, and you cannot trigger, direct, or modify a coronal mass ejection with a radio transmitter. The scale mismatch is not subtle. It's the difference between a flashlight and the sun. To put it another way, because I think the scale here deserves emphasis. If you took every HARP facility ever built, multiplied it by 1 million, ran all of them continuously for a year, and somehow focused all of that energy into a single burst directed at the sun, you would still fall short of a single CME's energy by a factor of roughly 100,000. The sun produces more energy in 1 second than humanity has generated in its entire history. The idea that a 3.6 megawatt radio array in Alaska is influencing solar behavior is not just wrong in degree, it's wrong in kind. It's like suggesting that a child with a garden hose is responsible for the tides. But here's where this gets genuinely interesting. At the one framing that has a real scientific substrate, there is published, peer-reviewed, actively debated science on whether human electromagnetic emissions interact with the near-Earth space environment. Very low-frequency radio emissions from power lines, industrial equipment, and military communication systems propagate into the magnetosphere. They interact with the radiation belts. NASA's Van Allen probes observed evidence that decades of VLF emissions may have created a kind of artificial bubble around Earth that subtly alters the behavior of the radiation belts. This is categorically different from the HAARP claim, nobody is steering storms, but the idea that human electromagnetic activity interacts with the space environment at some level has scientific traction. It's just not the traction the conspiracy claims are reaching for. The conspiracy explanation is wrong. The actual explanation is alarming enough. The sun is in an unexpectedly active cycle. Our warning system depends on aging spacecraft. Our grid has known, mapped, quantified vulnerabilities. That story doesn't need a villain with a button. The physics is sufficient. Part 13, the international dimension and the near miss. There's a dimension to this investigation that requires stepping outside the American monitoring framework because geomagnetic storms don't carry passports. ESA's Space Weather Service Network monitored the January event simultaneously with NOAA. Their assessment language was pointed. The event peaked at 1915 UTC on January 19th, reaching severe levels, and they explicitly called it one of the most intense radiation storms recorded. They linked it directly to the safety calculus for Artemis missions, a connection American coverage largely missed. The monitoring infrastructure for space weather is fragmented by jurisdiction. NOAA warns American operators, ESA warns European operators. Individual national services issue their own forecasts. There is coordination through the International Space Environment Service, but the speed of a CME doesn't wait for bureaucracy. The warning window is 15 to 60 minutes. Coordination happens in real time or not at all. The power systems of Northern Europe are as vulnerable as the northeastern United States, for similar geological reasons: resistive crystalline bedrock, long transmission lines, high latitude exposure. The January aurora over France and Belgium wasn't just a light show. It was a demonstration that the geomagnetic impact was continental. And behind all of this sits a near miss that almost nobody processed. On July 23, 2012, a CME erupted from the sun that was, by multiple measurements, comparable to the Carrington event. Daniel Baker at the University of Colorado's Laboratory for Atmospheric and Space Physics published the analysis. The CME's speed, magnetic field strength, and density were all in the range that would have produced a catastrophic geomagnetic storm if it had hit Earth. Stereo A, positioned along the CME's path, recorded it in full. It missed Earth by about 1 week of solar rotation. The active region had been facing Earth days earlier. By July 23rd, it had rotated past the Earth-directed window. The CME blasted into empty space. Stereo A happened to be in the right position to record the full passage, speed, magnetic field, density, all of it captured with the precision of in situ instruments flying through the plasma cloud itself. Baker's analysis, published in Space Weather, was unequivocal. The magnetic field strength inside the CME was extreme. The speed was in the Carrington range. If this structure had hit Earth's magnetosphere, the resulting geomagnetic storm would have driven DST values deep into the negative hundreds or beyond. The GIC levels in the North American and European grids would have been unprecedented in the satellite era. Transformers in the most geologically vulnerable regions would have experienced current levels that no operational test has ever validated. If that CME had launched 9 days earlier, it would have hit Earth squarely. The grid, the satellites, the communications infrastructure, all tested at a level never experienced in the modern era. We missed it by the sun's rotation, by luck, by the geometry of a rotating star, and almost nobody noticed. The event made it into journals and space weather blogs. It did not make the front page of any major newspaper. It did not trigger a congressional hearing on grid vulnerability. It did not accelerate the deployment of GIC blocking capacitors or fast-track the replacement of aging L1 sentinels. It just slid past, recorded by Stereo A, published by Baker, cited in subsequent risk assessments, and otherwise filed away as a near miss that the public never learned about. The May 2024 G5 storm deserves deeper treatment here because it's the closest analog we have to a severe compound event during the modern monitoring era, and the lessons from it connect directly to the January 2026 data. Active region 13664 was a monster. It was one of the largest and most complex sunspot groups observed during cycle 25, producing an X8.7 flare on May 14th, the strongest flare of the cycle up to that point. But the damage came not from any single eruption, it came from a sequence. Between May 8th and May 14th, the region produced multiple M-class and X-class flares, each accompanied by CMEs directed toward Earth. Several of these CMEs merged in transit, a phenomenon called CME-CME interaction that creates a combined structure with enhanced magnetic fields and compressed plasma. The resulting merged structure hit Earth's magnetosphere like a train of boxcars rather than a single locomotive. The geomagnetic storm reached G5 briefly on May 10th and 11th, with the KP index hitting 9 Dürers, the maximum on the scale. The interplanetary magnetic field reached magnitudes of 73 nanotesla, with the southward component reaching -50 nanotesla. Solar wind speeds range from 750 to 950 kilometers per second between May 11th and 12th. And yet, the grid held. No major blackouts were reported. Satellites experienced disruptions but recovered. The Starlink constellation reported some degradation. The aurora was visible across much of the world, including locations in the continental United States as far south as Alabama and Florida, creating a cultural moment. Millions of people photographing the sky and sharing images on social media. Why did the grid hold when the storm briefly reached G5? Several factors. First, the interplanetary magnetic field orientation was not continuously southward. It fluctuated. The periods of strongest coupling were interspersed with periods of weaker coupling, giving the magnetosphere and the grid periodic relief. A fully southward-oriented field, sustained for hours, would have produced dramatically worse GIC levels. Second, the storm hit during a period when grid operators had been warned and had activated mitigation procedures. SWPC had issued watches days in advance as the CME sequence launched from the sun. Third, the geological and grid conditions happened to be within the range the system could absorb. But the May event revealed something important. The aurora's visibility at low latitudes, distant subtropical latitudes, demonstrated that the geomagnetic disturbance penetrated further toward the equator than typical storms. The GIC effects were measurable across a broader geographic area. And the satellite impacts, while manageable, showed that a sustained event at this intensity or higher would begin to challenge spacecraft operational margins. The January 2026 S4 event followed the May 2024 G5 by roughly 20 months. Two events of exceptional severity within the same solar cycle. Neither was Carrington class, but together they demonstrate a pattern. Solar cycle 25 is producing severe events with a regularity that the consensus forecast didn't predict, and each event tests the warning and response infrastructure at levels close to its design envelope. If the cycle produces 3 more events of comparable severity before activity declines toward minimum, which is not unlikely given the observed flaring rate, each one is another roll of the dice. Another test of whether D. Escovier's instruments hold up. Another test of whether the CME's magnetic field happens to be oriented favorably or unfavorably. Another opportunity for the temporal alignment that distinguishes a manageable storm from a catastrophic one to tip in the wrong direction. GAC, Part 14, the first interpretation. The system is working. I've shown you a lot of alarming evidence over the past 2 hours. Now I owe you something harder than alarm. I owe you honesty about how to hold all of it. The case that the system is working deserves honest presentation, and I want you to hear it with the respect it deserves, because this interpretation is not wrong. The January S4 storm was severe. The grid held, the satellites held, communications degraded and recovered. Artemis II launched 10 weeks later and returned its crew safely. D. Escovier provided data throughout. SWPC issued timely warnings. Grid operators activated mitigation protocols. Nobody died. Nobody lost power for 9 hours. And this isn't luck. It's decades of investment. Hydro-Quebec spent $1.2 billion on grid hardening after '89. NOAA accelerated space weather monitoring upgrades after the Halloween storms. DSCO-VR launched as a dedicated sentinel. SWFO L1 is now at L1, commissioning its instruments. The modeling pipelines are faster. The alert systems reach more operators in more sectors. The forecast error on cycle 25 is real, but individual event forecasts have been largely accurate. SWPC knew the January CME was coming. They tracked the KP through G4. The information flowed. Someone holding this interpretation would say the risk is managed, not eliminated. They'd point to FERC reliability standards, USGS hazard mapping, GIC monitoring, equipment at vulnerable substations, and response playbooks that have been exercised. This interpretation rests on real institutional competence. It accounts for the data, and it may be correct. Let me make the case even stronger, because making it strong makes the other interpretations more meaningful by contrast. Consider the full scope of investment since the last major grid failure from a geomagnetic storm. After Quebec in '89, the response was not just provincial, it was continental and institutional. NERC, the North American Electric Reliability Corporation, developed geomagnetic disturbance standards that apply across the interconnected North American grid. These standards require transmission operators to conduct GIC vulnerability assessments, develop operating procedures for geomagnetic disturbance events, and maintain capability to respond in real time to SUPC warnings. The standards have been refined multiple times and carry enforcement mechanisms. TAS, NERC can levy penalties for non-compliance. The monitoring infrastructure has expanded dramatically. USGS operates a network of ground-based magnetometers across the United States that provides real-time data on the ground-level magnetic field, variations that drive GIC. SWPC combines this with solar wind data from L1, satellite measurements from GOEs, and output from the WSA NLIL and geospace models to produce geomagnetic forecasts that reach grid operators through dedicated communication channels. Individual utilities in the most vulnerable regions have installed GIC monitors on their transformers, devices that measure the quasi-DC current flowing through the grounding connections in real time. These monitors give operators direct visibility into whether their specific equipment is experiencing dangerous current levels, rather than relying solely on regional forecasts. The satellite industry has developed its own response protocols. Satellite operators can place spacecraft in safe mode, reducing power consumption, retracting sensitive instruments, adjusting attitude to minimize cross-section EW when SWPC issues warnings. The Galileo and GPS constellations have built-in redundancy that allows continued operation even when individual satellites are affected. The Starlink constellation's low-orbit design means that satellites experiencing anomalies deorbit relatively quickly and can be replaced from SpaceX's production line. The aviation industry reroutes polar flights during geomagnetic storms to reduce both radiation exposure for crew and passengers and the risk of HF radio communication loss. These rerouting procedures are well established and have been exercised during multiple events during Cycle 25, and the space weather forecasting capability itself has improved enormously. The WSA NLIL model, while imperfect, provides CME arrival time predictions that are typically accurate within 6 to 12 hours, enough to move operational preparations from standby to active. The geospace model provides GIC forecasts that, while they can't predict the exact transformer that will be stressed, can identify the regions where GIC levels will be highest. Add it all up, and the picture is one of layered defense. Warning systems at L1, solar monitoring from geostationary orbit, ground-based magnetometers, GIC models, utility operating procedures, NRC standards, satellite safe modes, aviation rerouting. It's not perfect, no defense system is, but it's vastly more capable than what existed in 1989, and it has been tested by multiple severe events during Cycle 25 without a major infrastructure failure. A person holding this interpretation would note fairly that every major technology system involves residual risk. We accept residual earthquake risk in California. We accept residual hurricane risk on the Gulf Coast. The question isn't whether residual risk exists, but whether it's managed to a level that society has implicitly or explicitly accepted. And by the evidence of the past 2 years, multiple severe solar events, no major grid failures, no significant satellite losses, a successful crewed lunar mission, the answer appears to be yes. This interpretation is not complacent. It acknowledges the gap between current capability and full protection, but it argues that the gap is being closed through ongoing investment, that the pace of closure is reasonable given competing priorities, and that the probability of a Carrington-class event in any given year is low enough to justify continued incremental progress rather than a crash program. I give this interpretation genuine weight. The people who hold it are not naive. Many of them work in the grid reliability community and understand the threat better than most commentators. Their expertise and their track record of managing the events that have occurred deserve respect. And yet the other interpretations exist for reasons the evidence supports, which is why this assessment presents all three. Part 15. The second interpretation. The gap is real, but here's the interpretation the published literature most directly supports. The system worked in January because January was not the worst case event. An S4 radiation storm and a G4 geomagnetic storm are severe, but the scales go higher. S5 exists. G5 exists. The system was tested at a level substantially below its design limits, and there are reasons to believe the design limits are insufficient. The transformer investment has been real but uneven. Canada invested heavily after '89. Parts of the American grid have not. The cost of protecting the 1,000 most vulnerable transformers is roughly $100 million, a rounding error in the sector's capital budget. The deployment is incomplete because the incentive structure is misaligned. A utility incurs costs now against a threat that might not materialize in their CFO's tenure. The warning system gives 15 to 60 minutes. Adequate for some responses, satellite safe modes, flight reroutes, transformer disconnects. Not adequate for all. You cannot evacuate a hospital in 15 minutes. You cannot inform 40 million people that their power might go out for weeks. The magnetic field orientation inside an approaching CME, the single most important parameter for predicting storm severity, George, is unknowable until the plasma reaches L1. Models can estimate it. The estimate is often wrong. And when it's wrong about southward versus northward, the error is binary. Minor storm versus severe storm. The gap between what the sun can deliver and what the grid can absorb is real, and it may be growing. And the FERC reliability standards, the formal regulatory response, deserve specific attention because they represent the formal regulatory response to GIC risk and the gap between what the standards require and what full protection would demand is illustrative. FERC Order 800 DUs, issued originally and then refined through subsequent proceedings, requires transmission operators to assess their GIC vulnerability and develop operating procedures to mitigate the risk of geomagnetic disturbances. Utilities must perform vulnerability assessments, establish operating procedures that include real-time monitoring during geomagnetic events, and maintain the capability to reduce GIC flow through at-risk transformers by adjusting system configuration. But the standard doesn't require utilities to install blocking capacitors or other hardware solutions. It requires assessment and operational response, meaning human beings watching monitors, making real-time decisions about which transformers to disconnect or which loads to shed. Operational response during a 15 to 60 minute warning window, when the forecasters at SWPC are simultaneously trying to determine whether the approaching CME has a southward magnetic field, when the grid operator is simultaneously managing normal system operations, when the communication between SWPC and the control rooms has to flow through whatever channels remain functional. This is manageable for a G3 or G4 event, the kind the system has successfully navigated multiple times. For a G5 that escalates rapidly, with a strongly southward field and a fast transit time, the operational response model starts straining. And for a Carrington-class event, where the GIC levels may exceed anything the operators have trained for, where multiple transformers may be threatened simultaneously across different utilities, and different regions, where the communication systems used for coordination may themselves be degraded by the storm. The operational model has never been tested. The gap between assessment plus response and hardware protection is the gap in this interpretation. The system works at the levels it's been tested at. It has not been tested at the levels the sun is known to be capable of producing, and the difference between those two levels is measured in transformers lost, in population affected, and in months without power. Part 16, the third interpretation, threading the needle. And then there's the interpretation I keep coming back to. July 2012, a Carrington-class CMA, missed Earth by 1 week, recorded by Stereo A, published by Baker, filed away, no public reckoning, no accelerated grid hardening, no fast-track Sentinel replacement, just luck documented in a journal. When I put that near miss alongside January 2026, alongside the forecast miss on cycle 25, alongside the aging warning system, alongside the transformer logistics, the picture isn't imminent catastrophe. I want to be clear about that. It's a picture of a civilization threading a needle it doesn't fully appreciate. The needle is temporal. It's the window between where our infrastructure sits now and where it needs to be. And the thread is solar activity, which follows its own schedule and has repeatedly demonstrated that our predictions of that schedule are unreliable. The moon absorbs every CME at full intensity. It takes the unfiltered measurement. It shows us the raw number. And right now, during a solar cycle that surprised the forecasters, the raw number is running higher than the benchmarks of the past 2 decades. The moon is the honest measure of what the sun is actually doing, not what the models say, what the physics is delivering to an unprotected surface. The temporal needle metaphor needs one more piece to be complete. The grid is not static. It's changing in ways that may be increasing its vulnerability to GIC, even as other investments improve its resilience to conventional threats. The transition to renewable energy, solar panels, wind turbines, battery storage is restructuring the grid's architecture. Distributed generation reduces dependence on long transmission lines for some loads, which could reduce GIC exposure. But the transition also requires new interconnections, new high-voltage direct current lines for moving renewable energy from where it's generated to where it's consumed, and new power electronics that may be more sensitive to the harmonic distortion caused by GIC-saturated transformers. Smart grid technology, the digital sensors, automated controls, and communication networks that make the modern grid more efficient and responsive introduces a different kind of vulnerability. These systems depend on GPS timing, satellite communications, and internet connectivity, all of which are affected by geomagnetic storms. A storm severe enough to disrupt GPS timing signals could cause the smart grid's own coordination systems to malfunction, potentially amplifying the cascading failure that the smart grid was designed to prevent. This is the paradox of modernization. The grid is becoming smarter, more efficient, and more capable of handling the variability of renewable energy, but it may also be becoming more brittle in the specific failure mode that geomagnetic storms exploit. The electromechanical relays and analog controls of the 1989 grid were crude by modern standards, but they didn't depend on GPS timing or satellite data links. The modern grid's sophistication is, in some scenarios, a liability, and the timeline for hardening the grid against GIC, deploying blocking capacitors, upgrading transformer monitoring, establishing strategic transformer reserves, is measured in years to decades. The timeline for the next severe solar event is measured in the sun's schedule, which has demonstrated repeatedly that our predictions of that schedule are unreliable. That's the needle. The thread is time, and we're pulling it through without knowing how much thread is left. Part 17, what we know and what we don't. Let me lay this out plainly. What we know: solar cycle 25 exceeded consensus prediction, smoothed sunspot number past 137 versus a predicted range of 105 to 125. 101 X-class flares by late February 2026. The January CME produced an S4 radiation storm, exceeding the 2003 benchmark. The KP index hit 8, G4 severe. The Moon's exosphere responds dramatically to CME passage. DSCOVR provides 15 to 60 minutes of warning and experienced a software anomaly in July 2025. Extra high voltage transformers are the critical grid vulnerability. Lead times for replacement run 12 to 18 months. GIC blocking capacitor deployment is incomplete. The July 2012 Carrington-class CME missed Earth by 1 week. Artemis II flew through the active radiation environment and returned safely. These are measured, documented, and not disputed. What we don't know: the full lunar exospheric response to the January CME, the peer-reviewed analysis is pending. The complete Artemis II radiation dosimetry, months from publication. The true return period for Carrington-class events, the estimate has wide uncertainty bounds. Whether the current grid hardening is adequate for a G5 storm during peak load with a strongly southward interplanetary magnetic field. Whether the DSCOVR to SWFO L1 transition will complete before the next major event. Each of these open questions has a specific data point that would close it. The LRO LAMP and Artemis publications. The Artemis II dosimetry report. Continued monitoring of the cycle. The SWFO L1 commissioning milestones. And the grid question will only be closed by a massive investment in hardening or by the storm itself. I know which of those I'd prefer, adding specificity to the uncertainty statements because vague uncertainty is worse than no uncertainty at all. On the lunar exosphere question, the TU Wien study established that normal solar wind sputtering is 10 times less efficient than models assumed. Killen's simulations established that CME sputtering should dramatically enhance the exosphere. The January event was the strongest radiation storm since 2003. The LRO LAMP instrument and Artemis probes were in position. The unknown is whether the observed enhancement matches Killen's predictions, exceeds them, or falls short, and the answer will reshape our understanding of how the lunar surface responds to extreme space weather. The peer-reviewed results should appear within the next 12 to 18 months, given typical analysis and publication timelines for planetary science. On the Artemis II dosimetry, the Orion spacecraft carried multiple radiation monitoring systems, including the hybrid electronic radiation assessor for real-time monitoring and passive dosimeters for cumulative dose measurement. The crew spent 10 days in the deep space radiation environment. The raw data is in NASA's hands. The detailed analysis will account for the spacecraft's shielding geometry, the crew's location within the spacecraft during different mission phases, and the specific solar particle events that occurred during the flight. The results will be compared against pre-mission predictions generated by the same modeling infrastructure that forecasts the solar cycle. If the actual doses significantly exceed the predicted doses, that discrepancy carries implications for every future mission beyond low Earth orbit during active solar conditions. On the transformer vulnerability, the Department of Energy identified the strategic reserve gap over a decade ago. FRC has issued reliability standards. Blocking capacitor costs are well characterized, roughly $100,000 per unit, $100 million for the 1,000 most vulnerable transformers. The deployment status is uneven across utilities and regions. The specific transformers at highest risk are identifiable from the USGS geoelectric hazard maps combined with utility infrastructure data. The unknown is not where the risk is or what would fix it. The unknown is whether the fixes will be deployed before the next event that tests them. On the warning system timeline, SWFO L1 reached L1 in January 2026. Its compact coronagraph, CCOR1, is producing differential imagery that recently became available on the SWPC website. Full operational capability, meaning SWFO L1 is the primary data source for operational space weather forecasting, with DSCOVR and ACE in backup roles, requires completion of all instrument commissioning, validation of data pipelines, and certification by NOAA. This process typically takes months to a year after orbital insertion. Until it's complete, the early warning system relies on spacecraft operating far beyond their design lifetimes. Each of these data points will arrive on its own schedule. The lunar science publications will come when the analysis is complete and the peer review is done. The dosimetry will come when NASA releases it. The SWFO L1 certification will come when the engineering is satisfied. None of these timelines are under anyone's control except the people doing the work, and rushing any of them would compromise the quality of the answer. But the sun doesn't coordinate with publication timelines, and the next CME doesn't wait for the last one's data to be analyzed. This is the fundamental tension in the story. The evidence accumulates at the speed of science. The threat operates at the speed of plasma. Part 18, Watching the Canary. I started this investigation with a shockwave striking the moon, and I want to end there. The moon is giving us something no other body in the solar system can provide from this vantage point. An honest measure, our magnetosphere filters the data. That's its job, to absorb, redirect, and diminish what the sun delivers. And it does that beautifully. But because it does, we never feel the full force. We see the aurora, we see the KP climb, we measure the GIC. But all of those are filtered through the shield. The moon doesn't have that filter. When a CME hits the moon, we get the raw measurement. Sodium and potassium atoms ripped from the regolith at energies that tell us exactly how hard the sun hit. Proton counts on the Artemis probes reflecting the actual particle flux. Surface weathering patterns that accumulate over billions of years as a geological record of solar violence. Right now, the canary is telling us the air quality has changed. The radiation environment is more active, more energetic, and less predictable than the model said. We have astronauts flying through it. We have a grid underneath the shield. We have a warning system running on borrowed time. And we have a scientific community processing data from a storm that hit the moon harder than anything in the modern record. What happens next depends on which interpretation turns out to be right. If the system is working, January was a validation. If the gap is real, January was a warning that the next event up the severity scale will be significantly more costly. If we're threading the needle, the question isn't whether the next Carrington-class event will come. It's whether we'll be ready when it does. The data doesn't tell us which interpretation is correct. What it tells us is what each one costs if it turns out to be wrong. The blocking capacitors cost $100 million for the 1,000 most vulnerable transformers. The economic damage from a Carrington-class event is estimated at $0.6 to $2.6 trillion. That's a ratio of at least 6,000 to 1. $6,000 of potential loss for every dollar of prevention. No rational insurance framework would accept that ratio without action. No rational engineering discipline would design against it. And yet here we are, threading the needle, hoping the sun cooperates with our procurement timelines. The moon doesn't hope. The moon doesn't plan. The moon absorbs. And the data it produces is the most honest assessment of the threat we have, because it's the only measurement that doesn't pass through the filter of Earth's magnetic shield before it reaches our instruments. This channel will keep watching. The LRO and Artemis data will be published. The Artemis II dosimetry will be released. SWFO L1 will complete commissioning or it won't. Solar cycle 25 will produce more outliers or begin its decline toward minimum. Each of those data points narrows the uncertainty. Each one tells us something about how much time we have and how much risk we're carrying. I don't have a clean ending for you. Clean endings are for stories where the investigation is complete. This one isn't. What I have is a commitment to stay on this, to follow the publications, to track the commissioning milestones, to watch the daily solar activity reports, and to tell you what I find, plainly, without embellishment, without conspiracy, without telling you how to feel. The moon took the hit in January. It will take the next one, and the one after that. 4.5 billion years of taking hits, and it's still there, still orbiting, still absorbing every eruption the sun produces. The question is whether we're learning from what it shows us, or whether we're watching the canary and walking deeper into the mine. And when the data arrives, we'll be here. Script: orbital view. Why the shockwave? Striking the moon, right now, has forecasters terrified. Format: prompt, 2C long format. Final integrated version: parts, 18, hook, version 3, the compressed arc,